Thanks a lot, Terry and Celeste, for making time to watch our crazy endeavors from this week. So I think each team has a short presentation prepared. I don't know, should we just start with team one?
Team one.
Was it you guys simulated?
It was Jumanji. Sure.
Team Jumanji? That's you guys?
Yeah. Oh shoot, I forgot the. Okay, so our project was myself, Jeremy Shoemaker, and Dale Schumacher. We've got the cobblers, Scott and the cobblers, as we call ourselves. They didn't.
Is that really, those are probably the same name, aren't they, one time?
Right. Yeah.
I never thought about that. Okay, that's pretty interesting.
Our task was to, well, for a while we've been wanting to move to this new simulator called MuJoCo, and primary reason is largely because we can't get out of Python 3.8, which is no longer supported. So as soon as we can ditch Habitat and move over to MuJoCo, however you want to say it, Jumanji, we can move on to Python 3.9, which is also no longer supported, but then very quickly we can get to 3.10 and to infinity and beyond. So how did it go? It went really well. So I'm going to show some demos. We were able to get pretty much everything. You know, we got the distant agent.
You set out with the goal to implement a no-op agent.
Yeah. We sent out
that in the first day, I think.
Yeah.
Right. So the running commentary for the judges, right? They said it's going to be really hard. If they're lucky, they'll get this no-op agent. And as Vivian just said, they got it done the first day. So what do we make of that? Are they geniuses or sandbagging? I don't know.
The truth is usually somewhere in between. So this is just showing what we would normally see in Habitat, but we're now using the MuJoCo environment. So the views we're seeing are from the sort of zoomed out view, and the little white square is what the sensor patch would see, just not being shown here because we didn't have time to.
And how, I guess, can you prove that it's not Habitat?
How can I prove it?
Installed or?
You can just lie.
It's actually not. It's not in the 2D environment.
If you open up a Python terminal and try to import Python, I have that on first in, it's not going to work.
Nice.
And is this then Python 3.9?
This is Python
Yes.
3.9. Yeah.
Nice.
And nice.
I'm sorry, just a stupid question. Why didn't you go to 310 if they no longer support 3.9?
That's a tricky question.
Just one at a time.
Yeah.
But
Just like climbing, have to maintain
oh,
3
you
points of
can't
contact.
you can't skip between three.
You can, but we don't hate ourselves. And we
Okay.
can do it one version at a time.
Yeah,
I don't
think
use that
relatively-
dangerously.
It should be relatively straightforward to get from 3.9 to 3.10. It's just
Yeah.
like,
I think it was there's like 5 changes between 3.8, 3.9, 5 changes between 3.9. That could be 10 changes at once. But
Yeah.
3.10 has some
But
big
this-
changes.
Remember, there's just like there was also like 5 changes from 3.8 to 3.9, and they've been added for trying to do that for 2 years.
Okay. So you did 10 years of work.
a lot of it's going to come down to like what
I just-
library versions
Yeah.
we're using and what versions they support.
All right.
Yeah.
That's a curious question.
Yeah.
The question is,
Yeah,
it's
that's
a
a
lot
good
of work.
question.
It's a lot of work, and you can't stop
Good
all this.
Yeah. So when we went to bed last night, we didn't have these goal-driven jumps. We were pretty much resigned to like, okay, we've got the distant agent, but no goal-driven jumps and no surface agent, and we've just under the wire got both the goal-driven jumps this morning and the surface agent working this afternoon. So it's basically full support.
That's
Wow.
great. That's what you're saying.
Woo!
Maybe you had it done Tuesday morning, and you're just telling me. Sorry. Great.
And
That's amazing.
yeah, so yeah, we're really pleased with how it went.
One more key feature,
What's that?
we are recognizing objects.
Oh, right. Okay, so let me get back to our I'll just get back to our slides here.
We have that, okay.
Right, so we've got the distant agent and the surface agent with the goal-directed jumps. And what's really awesome is that we were able to perform inference using the models that we had trained in Habitat successfully, which means that's like, it's
Sim to sim.
Sim
Yeah,
sim.
sim to sim, so,
Sim A to
like-
sim B. That is a new metric.
So for
Yeah.
context, it's a common problem for people to like train their models on one data set in one environment, and then when we bring it out into the real world or any other thing, it sort of breaks because it was sort of like overly fitting on this sort of artificial world. And this is awesome news both for the simulator, but better news for Monty because it means we're actually learning things that aren't so married to the very particular environment that we're learning them in. So that was a really awesome result to see.
Sorry.
That's like growing up in Legoland and then at 20 years old, put out the roof.
Yeah,
It survived.
right.
There
Yeah,
you go.
yeah. Or at least growing up in Duplo land until you're 5 years old and then you make a Legoland. Yeah. The next step is real world,
But yeah, just like if the pixels were just slightly different in some way or whatever, deep
Right.
learning methods will very quickly just be
fail. Yeah.
fail.
Because we're learning like no,
They're
yeah. I
really
don't want to say noise, but
Right.
learning. So that's awesome. So after this week, I'm pretty much off of it. I'm sort of back to normal, and then Jeremy will continue, his work, and it's a bit slow right now. Not really sure why, but I'm sure that'll get shaken out. Some kind of, I don't know if you have any hypothesis about that, but it's just some.
A bit is like what?
It's significantly slower, but I think it might just be something we're doing. We're not using the library for that
It
properly.
might not be using GPU right now or something. Okay, so yeah, just have to optimize it for the computer basically, and then
Clean up the code.
once there's
We're only doing,
clean up,
we're doing straightforward things that get us the solution. But our focus was not
Yeah,
performance.
yeah.
Right, so like I think if there was 5 sensors, don't we render the image 5 times instead of once?
I mean, I think we do that anyway with the Habitat version.
Okay.
But it's
Say, for
possible that
example-
Habitat's like doing optimizations that we might have to do manually.
Yeah, or like you say, just not using the GPU
Yeah.
stuff.
I mean-
Yeah.
That would be a big difference.
Honestly, we haven't even really looked into it. It's
Yeah, we
like,
haven't.
All the functions are implemented. Is that what you're saying?
Yeah.
And now it's just
Pretty much.
There you
Yeah, nice.
go.
And
Nice.
I guess maybe to convey to the judges that this wasn't just a case of like pip install MuJoCo, whatever. Do
No.
you have any photos of like the equations you guys had to work through?
Yeah.
Stuff like that. That was like some pretty,
Yeah.
I think Terry and Celeste were thinking it's just like Pip installed.
No, but like there was some pretty dense math you guys had to basically re-implement for this.
Yeah, we had to like redo all the coordinate transformations and how the actions are implemented and all that sort of stuff. So there's a lot of geometry, but we're all getting a lot of practice and getting better at that. So we're able to kind of crank it out. So I think that concludes our presentations. Anybody have any questions?
So wait, one question. This is something that is you guys are going to use and needed to be done anyway, correct?
Correct.
Okay.
Doesn't it enable Windows too?
Theoretically.
This was just like a,
We haven't tested it there, but yeah.
Theoretically, yeah.
just a.
Was it-
just a.
Well, is it right to say that we've known had to do this for a long time, but it was so bothersome to think about that we didn't do it?
I've been trying to work on
Yeah.
it for a while now.
Yeah, Jeremy has been working on it
Okay.
for a while already.
Uh,
And yeah, it's been kind of a big thing on our roadmap for a while that we need to switch to MuJoCo. And so
Oh, that's good then.
And it will have some other advantages, right? Because like in general, Habitat is a fairly obscure simulator. Part of the reason it's not getting ongoing support, whereas MuJoCo is a much more popular one. It has more features like soft body physics, different things that we may want to explore in the future, which weren't the primary reason for this switch, but
Yeah.
it'll be kind of nice side effects.
Yeah.
And it runs on Windows.
Runs on Windows,
Right.
And it was
Uh,
a CPU.
and it can be
Yeah,
installed
it
with
runs
pip,
on
right?
CPU.
Because that's one of the other thing we can only install with Conda right now. Wasn't this going to enable us to do
You
pip?
get a UV, right?
Yeah.
Yep, use GV.
Or you
Yeah.
Yes,
It'll be.
yeah.
It's like a big technical.
So
Yeah.
it'll be much easier for people who want to use Monty to with a few like with their command line, just install it and use it.
Yeah, so there are a lot of benefits from moving away from Habitat into MuJoCo.
Shed a lot of baggage.
Yeah,
We-
and what does MuJoCo stand for?
It's like, I forget, just looked at it earlier, but it's like multi-joint, something.
Object environment. Yeah, a lot of people do biophysics type stuff with it. You can do like tendons and like
Multi-joint
Like
dynamics
bodies,
with contact.
it doesn't like again like you said.
I was like,
like
what's the
Neil said,
code
it's not
part? The code is contact.
really our target, but it's
Could be.
cool that it's there.
Could be
Yeah,
fun in the future. Yeah.
yeah.
An example might be that, the
Conformable
contact
objects.
is it
actually.
has touch pressure,
Touch sensors.
like an actual touch pressure against a physical object.
Right, as opposed to the current finger, which is a depth
Okay.
camera that can
Just looking really close.
and the finger just goes like into things.
Right.
Although
Super realistic.
we were saying though, we gotta be careful because we have to get the physics right, because otherwise the finger's gonna move the object.
Yeah.
Yeah.
We can give it.
But manipulation
A
of it
ton of
is a
mass.
possibility too.
We can give it.
Very heavy.
I mean, that
stack
might,
pad.
isn't that like part of learning an object though? It's like,
Yes.
wait, it moves.
Like a black hole.
Yeah. Yeah.
I don't know.
Yeah,
Good.
awesome.
Nice.
Yeah, this was a big success.
Yay.
Much.
Good job.
Goodbye.
Yeah, even like the surface is super. There's a lot involved in that.
Yeah.
Impressed.
Radiology?
Almost registry. I should unmute myself. Okay, never mind.
You use that much.
Can you hear me okay, even if I speak here?
Yeah, you're fine.
Okay, thank you. Let me put it in presentation mode first and ensure that issues.
It's pretty cool you guys finished it.
Yeah, I was surprised.
Yeah.
I expected like just loading the objects to be a pain in the ass, and it didn't end up being a pain in the ass. It was pretty straightforward.
Yeah, so unfortunately, we didn't have the benefit of having Scott, who is great at naming things, so our team name is something
Kind of
config.
accomplished it.
But it is descriptive enough that you know that we have worked on configurations. So this is Team Jose, Ramy, and Tristan. So the inspiration of this project for me came from Jiro. Jiro dreams of sushi. He's a master, I think, sushi chef / Michelin star in like a very small Japanese like Subway. And instead of Jiro dreams of sushi, Tristan, Jose, and Ramy have been dreaming of movies.
Wow, that's a stretch. Okay.
See?
He was also cruel to his son.
Well, okay, well, not kids. Yeah. So
I kicked my dog.
Arthur is sick right now, and I'm not there, so I guess so here's a snapshot of what one configuration looked like. What is this? Only surf agent training 10 object. You know, it's so small that you can barely see. And it has to define all of this stuff. And to understand this, you have to know all of this stuff, because all of this experiment depends on all of that experiment. And it seems like actually all of this experiment also depends on another one that we forgot to put.
Yeah, so what what you're saying is
Config.
the thing on the left, one element of that is basically the thing on the right,
Yes.
but the thing on the right is nested even more.
Yes.
There'd be like a dozen of these.
Yeah. So
And how do people do this today? They just cut and paste and edit? What's the?
Look at it and think really hard, and then type everything in.
Find the file.
yeah, you
find
can
the
see
file.
why it's hard.
Well, I'm just trying to understand what you have to do. It's like you have to, you start with one of these and then you modify it.
Yes, I'll show it. I'll show them more detail.
Okay. Yeah. So anyway, so these two screenshot now goes to this screenshot.
Beautiful.
You
can see there's much easier structure. So you know that when you're configuring an experiment, you want to configure Monty. That should be obvious. Like it's intuitive. You want to configure the motor system. You want to configure the learning module, the sensor module, the connectivity. That's how we conceptually think about Monty. And you have to configure the environment and whatnots. And also by immediately looking at the names, I know some of the acronyms are a little bit esoteric, but you can immediately see, okay, this is a graph, Monty for graph matching that will do 1,000 exploratory steps, minimum 3 evaluation steps, minimum 3 training steps with a total of 25,100 steps. So yeah, you have to look at this file if you want to get like a full thing, but it should be very obvious from title what the parameters are, even without looking into it, right? So yeah, and then I will actually hand it off to Tristan so he can actually show you the real benefit.
Yeah, so just a quick demo of what you've seen there. So it's a little bit closer up. So these are the two files that are required to comprehend that one configuration. So this file refers to this other configuration that we can look at later. But what you're seeing here is use this other configuration and then override this one setting and override this other setting and override these other settings and override this other setting.
Showing, right?
Hopefully you're keeping
Yes,
up.
this is the old way.
Hopefully you're keeping up with what we overrode with what. And then after we get here, then we override it harder with these things. And then we override some more. And so in order to understand what this does, you have to understand all the overrides that you did here. And then you also have to understand this one, which also
This is the
inherits some
the other
stuff.
file.
Yeah.
This is the other file, which clears something and overrides it and overrides it. So we pretty much gave up on understanding. So actually, Jeff, to answer your question, we pretty much gave up on understanding this, and we just render the full thing, like the final configuration, what it looks like. So we have like snapshots. This would be only surf. So we end up with like just rendering the snapshots and just reading through this type of configuration to see what we actually put together. And every time we want to change it, we would kind of have to change something here and then verify that it did it correctly. Versus now, again, what Fudge said, we have a simpler setup. So the idea is, what I want you to think about is a new person coming into Monty, and they're like, I want to run an experiment, and I want to run my own, and what they have to comprehend in order to put things together. And so this is much easier for a new person to come through and understand than the previous version. So
Is there an underlying software package that you're using to help you with this, or is this all code we wrote ourselves to do? So
This is
Just-
based on a packet configuration package called Hydra. So Hydra is a package that will actually compose all of these together into the one final snapshot that you saw Tristan share. So we can say, oh, I want the learning module piece. I have written a small learning module piece, the short YAML, a short sensor module configuration, and Hydra is responsible for putting them together.
And one thing about Hydra is, but I want to highlight that both of them use Hydra. This is Hydra, and this
Used in a bad
this
way,
is Hydra
I'd say.
used in the way, like this is the direct translation of our configurations used to look like. And we just translate them to Hydra as the first step. And then this is the second step of actually using the Hydra as intended.
So I'm just trying to imagine what the actual work you did to make all this lovely benefits. We just like reorganizing how you're using Hydra.
What was it? 300 commits?
Yes, we have made.
Wow.
Just
Moving stuff
so
around.
yeah, so I think that's the next slide actually, the work.
Yeah, let's just go back to it, yeah.
Wow.
Yeah, there's quite like a lot of deliberate thinking about like it wasn't.
We rewrote
you had to make
every
a lot of choices
configuration by
about
hand,
how to structure.
So
it.
did were you
Break
like
up.
writing a config for Hydra? I'm trying to understand what's going on.
Yeah,
We had to rewrite all the configurations so that we took snapshots of every configuration that existed,
Uh-huh.
and then we rewrote everyone and made sure that what the new configurations generated matched the previous one
Uh-huh.
for all the benchmarks and experiments and for all the tests.
Seems like a lot could go wrong.
Yes.
Yes,
That's why you need the
But nothing went
snapshots,
wrong.
so you're not
but
changing.
nothing went wrong and all the tests passed. And
Yeah.
what was the?
Yes, yeah.
Would you guys say like it's done?
Yeah.
Or complete?
Pull request ready.
Right.
Wow.
To merge to TBP Monday.
Yes.
Yeah. Like we'll
Cool.
probably do it 2 weeks from now.
Cool.
Yeah, because I think at the beginning of the week you said you're gonna just prototype it at first
Right.
and see, but so now you're saying, yeah, it's the prototype works and we want to integrate it like that, and it's pretty much ready to integrate.
Yes.
So geniuses or sandbagging? What's the
So when you say you migrated 131 configs, each one had to be done one at a time?
Yes.
Yes.
I mean, and were any of them like trivial, or they all like a lot of work? I mean, it's a lot to do even for 3 people and you know. 5
Yes,
days.
so, okay, here's how it usually went. So, yes, toil. First of all, I was awake from like 1 a.m. but since 1 a.m. for most days, 2 a.m. So we had a little bit of a time advantage, I would cover from 1 a.m. to I guess 1 p.m. Tristan, I would overlap with Tristan from 8 a.m. to 5 p.m. and then Ramy is 4 hours before us.
This is surely gonna impress the judges.
Yeah. Yeah, but okay, so
Everyone else worked 8 hours a day, we worked 24 hours a day, 3 shifts.
yes. I mean that is truly one thing, but the other thing is, so we would try to refactor one config that will create some small learning module config. Maybe that uses displacement GraphLM, whatever class. But then when we start refactoring the second config, we notice, oh, this one is also using displacement GraphLM, so we can just actually use that component. So the second one would be faster because the component already exists.
Mm.
And then we go to the next one, maybe next one we have to actually create a new learning module config because it's not displacement GraphLM, but it's evidence GraphLM, whatever. And we just keep going until we create new ones. That was the general process. So yes, we did 131, 131 by hand. We have tested all of them. There's no changes from the new configs to the old one, which means that all the benchmarks and yada 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 will be are the same. I've actually read them.
Oh, nice.
Nice, yeah.
We have made 286 commits as a team and have made 747 file changes. So thank you to whoever will review this. Yes.
Yeah, so there we go.
Yourself.
Yeah, we could say like
Yes, like that.
yeah.
It sounds like we're not done yet.
Looks good to me.
Yeah.
Why do you have to review them if they pass the benchmarks?
And if it was
Yeah,
Yeah,
pair program.
Isn't a benchmark in some sense a proof that you did it right, or am I wrong?
Yeah, but like you can get the benchmarks right, but you still have to read every code line by line to see what's in there.
But did you guys do the commits together? Like, was it kind of pair programming or not really?
Yes, not really, but also this is prototype work. Like we're gonna review it one more time before integrating it into the stable platform and integrate the baseline on which everything else will be built from now on. Like it's okay, we can wait another week of review.
So I'm just curious how this works. So you passed the benchmarks, which sort of, in theory, that's the acid test for whether it works.
Yeah.
Yes.
So then the code review would be more like, oh, you did this a sloppy way. There would be an easier way to do it, or a better way to do it, or a cleaner way to do it. So in the future, if other people working on it might find it easier to understand or something like that.
Yeah, exactly. Like a product is the code itself.
Right.
And because we're open source and we want
Yeah.
other people to understand it. So part of it is making sure that the code itself looks
Okay.
presentable and understandable. So.
Can I give another example? So there's another way you can fail, which is you include something that doesn't affect the benchmark,
Right.
but it doesn't mean anything and it's ignored, but it's junk. You don't want that
Right.
laying around.
Or you could have mentioned introduce an error that just by chance none of the benchmarks hit.
Yeah.
And
That's less likely, but it's still
less likely, right?
Right.
Yeah, I understand it, but again, it's more of a like, this is a product, we want it to be clean and proper and all that kind of stuff.
Right.
How much work that review as compared to the work you did already?
It's gonna be a lot if it's somebody not familiar with, so that's why we're probably gonna just review it once more with one of us familiar. So like Claudio will probably do a PR and then Ramy and I will review it.
And is that quicker than actual writing it? I mean, is it?
Actual writing.
Review is
The work,
quicker.
I'm just wondering have you done 90% of the work or 80% of the work or 10% of the work?
Oh yeah,
It'll be quick for Ramy and I to review it.
Okay.
yeah, for sure. Yeah.
We also built tooling to compare the snapshots, so we have confidence that in the difference. But if it was somebody unfamiliar, it would take them a lot longer to review.
So I'm gonna cut this be so short.
Ooh.
One more thing to show.
Okay, Globo.
So we noticed that team one had a great idea to build a GUI. For example, I was quite interested in that as well. Here's us. And off to Ramy.
I know this.
Oh.
So
I'm sorry, I know that visual joke, but I didn't see the correlation to the visual joke and the teams. I missed that part.
it was each team had project proposed.
Oh, you're admiring the other team's project.
Yes.
So
Yeah.
they were looking at an idea that the other team had proposed,
Uh-huh.
and basically taking their proposal and implementing it
Got
as
it.
well.
Right,
Yeah.
right.
So,
Yeah.
all right, Ramy,
Yeah.
show us the magic.
Awesome.
You hear me?
Exciting.
Yeah, we can hear you.
This is a
Yeah,
surprise. I
perfect.
haven't seen this before at all.
So yeah, so the configs that we already have created, these are great configs, but we've created a tool, a terminal user interface that all of us could use, but also the community could use, and they will be able to create new configurations, explore the existing configurations, modify them, assign, deassign, and basically also understand how the configurations work, because our configurations are hierarchical. So let me just show you what it would look like. So this is my terminal, and I'm just going to start the tool. And it's a graphical tool, but it's for terminals. So what you see here, we have two windows here, two panels, and this is what the user will interact with. And then there's a viewer over here on the side. So this is what the actual files look like. And later I'll show you also some more features with things that you can show here. So this is the entry point for defining a configuration or looking at the country configurations. So the way this works is that for every, this is defined hierarchical. So an experiment here, you have to choose the experiment that you have, that you want to work with. So every item here on top has a bunch of variants that you choose from. And the way that people are going to be using it is just choosing from the variants that we have provided, or they can create their own new variants, and this tool can do both. So basically, first we have to start with basically selecting a variant. Once you select any variant, let's say go with this base 77 object destination. This is one example of an experiment. You can come here and look at it. Once you select it, you're going to be able to open it up and take a look at what is defined at the second level of the hierarchy, right? And these are the things that basically Tristan and Jose were showing. These are the defaults that were in the files. You can explore. You can go to lower levels of the hierarchy, and you can even go to even lower levels, depending on basically the structure of the experiment. So I'm gonna walk you through basically a newcomer experience, someone who just learned about Monty and he wants to, or they want to basically create a new experiment. So I'm gonna remove that assignment. We have a template here called My Experiment. This is basically an empty experiment template, right? I'm going to assign it to the experiment that we're running. And now we have all these modules that we just want to plug in. And building a configuration is just as easy as going through each one and choosing what variant you want. So it says, so let's say for Monty here, I'm going to go to the variants and I'm going to take a look at what class and arguments we want. And it's as easy as choosing the one that we
You're
want.
moving on the bottom left there, right? And the stuff on the right just reflecting what
It's like building.
Yes.
Yes.
Yeah.
Yes.
The left one of those, and it'll stick it up there.
Yes. That's correct.
Yeah. So I'm just going to choose this one for now. Yeah, just you can choose any of those that match what you're looking for. For the motor system config, we have a bunch of different configurations that we could use. And the thing is, some of these are hierarchical, like I showed before. So in the actual file, it may not show what this means, right? It says that, okay, this is the informed 5 goal 1, but I don't know what that means. And even in the file, it says, okay, it's just using the policy informed 5 goal 1. So what we also added is a way to resolve the configuration at this level by flattening it out. So you can see everything that it inherits from, and it just resolves. So you could just, if you hit V, it shows the resolved view, which basically shows you everything that's inside this option. And you can toggle it on and off. Now, the problem is sometimes you also don't understand what this means. Like in informed goal 5, goal 1, informed 5, goal 0. You don't know what goal 1 and 0 means. So you might want to have a diff view So you want to have basically show the difference. So if you click W, or like if you hit W on any of those, it will define the source for the diff. And then you can go to any other file, and it will just show you what the differences are. This works at any level in the hierarchy. So even between experiments, if you want to see the difference between the resolved experiments, you could do that. But now it's doing it here at this level, and it's just showing that the policy is different, but you could also resolve that, and it will show you the difference between the resolved files. So that basically says, okay, goal 0, going from goal 0 to goal 1, it adds that we want to use goal state driven actions. Now let's continue with this election. So I'm going to choose, maybe I don't want the goal driven actions. Learning modules. Okay, we have a bunch of learning. I know that I want to use evidence. So let's just simplify this. Let's filter by evidence. So I'm going to filter this by evidence. And we have all these evidence ones. Okay, let's choose NN5 DOD, whatever, right? And you can also show the difference between this one and that one, and you will see that the differences in the DOD basically stands for desired object distance, and we can use any of those. Let's use this one. I'm gonna go faster here a little bit. Camera distance, noise, raw 0. I know that the difference here between raw 0 and raw 1. Okay, that's just saving the raw observations. So you don't have to rely on the naming of the variants. You can also view the files and know what the differences between them are. So you can do this. Connectivity, I know that this is a single learning module. Let's just use a 1LM, 1SM. Interface, see, these are compositional ones, and I can see that also by the parent-to-child mapping and all of that. So I don't want to use a 77 object experiment. Let's use this one, which has these objects. And let's choose random rotations. Transforms. Again, these are all things that we know about Monty and things that we need to define. Let's use this one. Logging is easy. Do I want to use basic logging? I want to use detailed logging. I could choose whatever I want. Let's go with this one. And then environment. Okay, that's interesting. There's a couple of different. So I don't want to use the 2D data. I don't want to use test variants. I want to use habitat, but now it's interesting. I see that habitat YCB and habitat distance, I don't know which one to use. So let me just check the diffs between this one and that one. And I can see that the difference here is in the data path. This one doesn't take a data path for YCB, which also tells me that this habitat distance agent is probably only used in test in unit tests because it doesn't take YCB, which is something that I can also validate by this new feature, which is it tells you what references are. So what experiments use this one? There are a ton of features here. Like if you want to rename something, it can tell you warnings that is being used by something else, or whatever. So especially if you're renaming something in a hierarchy, lower in the hierarchy, it can tell you. I'll show you in a sec. So let's just, I don't know, I want to choose this one because we're doing inference and this is not a test experiment. So let's just do this. And now we have an experiment, my experiment. So let's run it, run parallel. And notice I don't have to give it the experiment name because I already added it to the configurations. So if you're iterating, if you're a researcher or someone from the community or someone using this, you can iterate over it by just like you define the experiment and you just keep saying Python run parallel without having to give it the experiment name. But anyway, it's running. I don't have to do this. So yeah, there are a lot of other features, but there are some features like if you try to delete something. So for example, I know this one is being used by other experiments. If I try to delete it, it will tell me, are you sure you want to delete it? It's used by all of these, yes or no. You can also create a new variant here. So you can do anything with configurations without actually leaving this tool. You can create a new variant. I can do this, duplicate. I get a copy of it. I can rename it. Rename it to, I don't know, 7. I can even edit it. I could go into the editor and change something in it. And once you go back here, you can try to assign it here. but it will tell you, it's being used by something else. So if you want to assign it, you can go. Yeah, it's a hierarchy. So if it's being used at the lowest level by something else, then you might want to create other files at higher levels. But that's an advanced use case.
What's the difference between two experiments? I want to know exactly what changed from base config, this 10 distinct object, this agent, to this agent, please.
So let's say from the base distant to surface agent for this one, you could do.
Absolutely. That's how you implemented it. It's a chatbot.
These are the changes from like base 77 distant agent to surface agent. You can even see the result, because this doesn't make a lot of sense here. If you're looking at it at the highest level of the hierarchy, it doesn't make sense. You need to resolve both of them and look at the differences. So yeah, you could just do this, you could resolve it. You'll see, these are the actual differences between the results configuration.
Also the differences we all memorized by this point.
Right.
It's really great.
We read the matrix, we see it, and we'll be like, oh, this is
This is a red dress.
distance LM1, 1LM.
So Ramy, had you started on this project earlier, or is this from scratch?
Is there a
from the
fourth
first-
team member?
No, or is this like you? Start from scratch?
We worked on it similar to, I think Scott had this idea of creating a configuration helper, and I also had this idea. I was thinking about the same thing, and we ended up working on it only during the hackathon, but I had a lot of help from AI, or AI had some help from me.
So you didn't really have, you hadn't started this before?
No.
No.
Just planning and thinking about it for a while. But it wasn't really possible without this new configurations stuff, because it was just very difficult the way that it inherited from different
Yeah, actually,
Yeah.
even if you were using Claude, like when were you able to start on this? Because as you say, it kind of depends on the changes you guys made this week.
Yeah.
Yes.
exactly.
That's
But also
Yeah, so that was the question. When did you start on it? Like by
Yesterday
yesterday
or-
yesterday?
update on Wednesday. I think there was a primitive version on Wednesday or Tuesday.
Yeah, because like Monday, Tuesday, we put in.
We were
I
just.
don't know. I don't know.
So
Ramy, when did you
I
start?
didn't hear the question. When did I
When
start?
did you actually start working on this? Like you said, it was kind of dependent on the changes
Yeah.
you made this week. So was it Wednesday or?
Two days ago. Yeah. So this took 2 days. But during these 2 days, Jose and Tristan were working very hard on the other stuff. I was mostly working on this.
What's the plan for this tool? Will it be inside TVP Monty tools
No.
or outside of Monty?
Outside of Monty.
Okay.
Tristan.
For
It's
now?
a different language.
Okay, yeah.
Yeah.
No, so it's something that you can install with Homebrew. Just brew install. We're probably gonna put it on a different Homebrew tab, but it's you can install it with whatever package manager you're using, so you can use it outside.
Is it Golang, Ramy?
It's Golang, yes. And also Vivian, I know that the way you like to create configurations is by inheritance or like copying something. So
For you.
basically it's the same thing. You just duplicate an experiment and you go to it, assign it, and modify it, and then you'll be able to do the diff between them. So let's say I want to just change this one to change the logging from detailed, from basic to detailed. You could just do that, and then that's it. You can see the diff between both of them is that it's just
There's no inheritance.
it's a fake inheritance, but yeah, you clone it and modify it so that you're sure that only the things that you changed are there.
Yeah, I mean, I'm not huge on inheritance itself. It's more the feature of knowing this is the only thing that changed between.
Yeah.
It's like a diff.
Yeah, like the diff can change.
we have a very rich diff. So
Yeah, that's super
that's
cool,
awesome.
Ramy.
Thank you, Ramy.
That's really awesome. And yeah, it's got no idea. Perfect.
So that's all we did.
Yeah.
Wow.
Yeah, this is it.
Things have made it hugely forward in the past few months.
Yeah.
Yeah. Any questions from the judges?
I just realized I wasn't sharing. Was I sharing all the time? When did I stop sharing?
No, you're protecting.
Up in the kitchen.
Oh my gosh, is that Ramy? He's like,
You're good. You stopped sharing now.
Okay. Good.
We were just listening to you and imagining.
Ramy, where
Yeah,
are you?
someone should have stopped me.
Where are you now, Ramy?
Florida.
What was it? Was it the purpose of trying to make something easier for Monty users?
Yeah, definitely. So we have a video of Tristan putting together like a 30 minutes with like it's a complete like 30-minute video of just trying to put together a full configuration. This is this just shows how the new configuration makes it a lot easier to put together just from scratch. It didn't take 30 minutes. It just took a few minutes.
So using the old way, how quicker is it for somebody or somebody new to be able to do it now? What's the time difference between what was and what your new one is?
It's a huge time difference. They should have started.
Like now, if somebody tries to do it instead of days trying to figure it out, it's 30 minutes.
There are two aspects. It's the once you understand the configuration is easier. You can do this with file editors and just keep changing stuff and doing all of that. So there's the aspect of rewriting all of the configurations to make them easier, but also this tool just adds it's like just an added new feature that makes it even faster and easier. So I would say the old configuration would definitely take days to understand. Like I still have trouble following all of the inheritance and all of that. So for someone new, it would definitely be very difficult to understand the configurations. Now it might take an hour or something to understand it, but this makes it easier to just build it very quickly. So there's
that's a huge difference.
Definitely less error prone. Looks like it was both the simplification of the configs and the tool you were showing probably because it definitely happens that we're running experiments day to day. Some parameter changes for whatever reason, or doesn't change the way we expect, and that again can cost days of we get a result that we didn't expect, and it takes us a while before we realize why.
Yeah, great.
So it'll make it a lot easier to switch the configurations up.
Yeah,
It's just like that environment thing.
and it is something people in the community often comment on the forums and stuff. So like, this is really confusing.
Yeah.
Cool.
Nice.
Yeah, I feel a bit bad for presenting.
Yeah, it's not act to follow.
Yeah.
yours would go and go in.
It's Golang is what people usually search for because Go is such a common word. It's hard to find.
Okay, I need to share.
But the language is technically called Go.
All right. We're 3 brains, 2 whiteboards, and a Christmas tree. We don't know how the Christmas tree joined our team, but
I was going to say,
It was a useful object occasionally to refer to in
yeah,
brainstorming.
it's here right now blinking in the background.
is it the only Christmas decoration in the whole place?
Yeah.
Yeah.
That's so bizarre.
Anyways, so when we started on Monday, we had kind of 3 ideas of what we could work on this week. We said we could work on open questions around voting, or we could work on modeling object deformations, or we could work on causal interactions with the world. And then we sat together and we talked about all of them, and we decided let's work on all of them. And our plan was for each of these 3 topics to exactly define the problem, list some examples, and then list some potential solutions. And as we do that, maybe explore some of the potential solutions in a bit more depth. And yeah, throughout this week, we actually talked about several more topics. We think we have a good understanding of what affordances are now, like in the brain. We're going to talk about that in a bit. Shared learning, we talked about a potential solution. forking models, the interaction between Cortex and Hippocampus, and we bought a big whiteboard. Oops. Oh, double. Yeah, that was our first action on Monday.
Well,
We
after we
decided-
used a little whiteboard for a while, one of you said, maybe we should get a bigger one.
Yeah.
But
and it made
then
a
when
big
it
difference.
arrived, we got a bit nervous because we were like, are we actually gonna, fill this thing? Or
We got
you know,
used to the small whiteboard.
yeah.
But then, yeah,
It
it
was
made a big
definitely worth it.
difference once we got it.
This whiteboard, by the way, folds in half, and then you have to put like screws in it. The whole
And you can flip it over.
Right.
Anyways,
Many affordances.
yeah, Niels, I think that's
Yeah, and so in general, we made lots of progress on all of these. As Vivian was saying, like the key thing we wanted to make sure we did for everything was defining the problem, listing kind of instances of the problem, and then just making sure we covered the space of the solutions, because often we kind of forget about what we've discussed or kind of forget how they relate to one another. But yeah, a lot of them we went into some detail about the solutions we'll talk about in a bit, but this included, sharing locations, kind of and how that relates to voting, this big problem of deformations, and then arguably this really like the biggest problem we've been recently dealing with, which is causal interactions and goal planning.
Yeah, and so I mean we have pictures of whiteboards and whiteboards and whiteboards. And it will take probably several research meetings to kind of talk about them all and present them in detail. So here's just a brief sample of some of our new ideas that we had throughout the week.
So to promote ourselves here a bit, the year
Yeah, you better.
we had a big research meeting. We came up with one big idea, which is behavioral models.
Yeah,
I think we've done at least 3 or 4 of those this week.
that's true. Yeah,
Right.
we had several large ideas.
These are not little ideas. These are like, oh, we fixed this out. We figured this one out. We figured this one out. So I'm not trying to tell the judges anything. I want to share the excitement of this, because for me it's very exciting. I think all
Right.
of us should be very excited.
Yeah, I mean that kind of aha moment we had last February and on the last day, that was a big one that like drove us through most of the rest of the year. And then
We've had like
Time
one a
with
week, one a day here.
yeah,
It literally is like that.
yeah, it kind of felt like a lot of things were falling into place. And then also looking at several topics and switching to them, we made some connections between them, and
Yeah, there was ways where one solution for one thing, it was like
help the other one.
fit perfectly well with something that came up later. So it really felt like it was like it's one of those things that just feels like it's fitting the brain, because the kind of constraints and the solutions are kind of mapping together and not kind of
And we've often talked about how progress is very, very slow in the beginning of something like this. You don't even know where to begin, like understanding how the brain works, and you can go for years and make no progress. Then you make something, and then the advances start accelerating. So it felt like today we're on a jigsaw puzzle. We're rushing to fill in the last pieces that we're going along, and now we're done. But it was really accelerating this week because we had so many other pieces in place already. We couldn't have done any of the things we did this week if we didn't have all other theories figured out. Right? So we're really seeing rapid progress. And I think it made a huge difference for us to be in this room together.
Yeah, and to have the big whiteboard.
And
Yeah.
by the way, but
Okay, so here's some of the big insights and new ideas we had. So one, we were thinking a lot about voting, and so right now in Monty, how voting works is that we have kind of all-to-all connections between the different columns, and each column that votes with another column needs to do a reference frame transform. So we have a lot of different reference frames transforms happening all over the place, but for every of these connections, we have to transform reference frames, and we just don't think that's realistic to be happening in the brain. It's something that works for now in Monty, but we've always said this isn't really the ideal solution, and there must be a better way of doing this. And so,
and I guess we knew something like this would be important, because clearly when we see everything all at once, we can use spatial information to kind of recognize what we're seeing. Like this is the kind of thing we don't do bag of features recognition. We understand space even when we sense things all at once, like putting all our fingers on one. So something like this had to be happening, but this solution just didn't seem right.
If you're not familiar with the old voting, the original voting we talked about before with Monty, it was just voting on ID, which is like a bag of features. Everyone's trying to agree on what object we were observing. And this is really saying, we know we have to take advantage of where the different sensors are relative to each other. And we have a solution in Monty,
Yeah.
but it's not the right solution. We think.
Yeah. And so new kind of some more clarity we had this week was one, just defining the problem and agreeing that this is not how the brain is likely not how the brain would be doing this. And secondly, we kind of came to the conclusion that one, it likely requires a shared location space. So if we don't want to have to do one-to-one reference frame transformation for every column that talks to every other column, we need to have some kind of shared location space. And then two, there will likely be a serial solution. So we can't broadcast them all at once, but you have to kind of go through them. And so one idea we had was that after each of these patches receives their actual sensory input, this kind of common space that got where all of these sensors are currently sensing in space does a rapid replay of those locations and broadcasts that to a wide range of columns. And that way, all of the columns for each of the fingers would receive all of the 5 locations as input. It would be kind of like getting an actual location and feature, and then quickly getting a couple of simulated extra locations from the other columns. And a bonus feature is that it can also solve shared learning, because you can imagine that this broadcast signal also going to your other hand, which is currently not sensing anything, it could still be learning about the shape of the cup.
And all those other models that, well, I know I live in them.
And yeah, this shared learning problem was also always a big open question that bugged us for years, saying, okay, I learned something with my eyes and I can infer it with my hand without ever having learned it with my hand, or I can infer it with my toe without ever having touched an object with my toe. How does the column connected to my toe know about a coffee mug? And so, yeah, it was kind of nice that
my middle finger knows what my left finger's feeling, and that kind of stuff. Right?
Yeah.
Yeah.
And that question came up over and over again for years, I guess. And now this could be a potential solution to it.
We don't know all the details of this, but we've convinced ourselves this solution exists in this direction.
Yeah.
And so that just knowing that is a big deal.
Yeah, like we don't know where this shared space would be in the brain, for example, or the exact mechanism of how it would be broadcast. We're pretty sure you could only broadcast a couple of locations. Like you couldn't broadcast like thousands of them in between sensations, but maybe like 5 to 10. But yeah.
Yeah, I think you can answer my question, which was
like how many?
well, where do are columns still storing the whole object models in this?
Yeah.
in this-
Yes.
Okay.
Yeah, this is kind of a way of like, it's almost like a buffer that stores the locations coming in all at once and then rapidly replays them to kind of simulate movement in everyone.
Your direct question, it makes no changes at all to the models in cortical columns of the line, not whatsoever.
Okay.
It's really a matter of how do they share more than just the idea of the object? They need we know this. They need to share information about the relative positions. We've implemented a solution to Monty, but we don't think it's biologically correct. And it also has problems even as a machine learning tool. So now we've convinced ourselves this is alternate direction is the way to go. And even if we don't have all the details, yeah.
And speaking of some nice synergy between the topics we covered, this has, a really nice outcome. So a lot of you may remember sometimes we talk about the inputs to the cortical column or to a learning module as being a location, but then there's also this displacement that happens, and then the output is a location. So the reason we do this right now, well, the key one actually is because of voting. So in order for the columns to be able to communicate spatial information with one another, given the way voting is implemented now, they basically need this common coordinate system. They need to know like, oh, I'm this far away from you. But the method we just described before gets rid of that. And that's really cool. It breaks the chains. It breaks the chains.
If we don't need voting on location anymore.
If we don't, it breaks
the chains.
Breaks the chains of passing in this location information, and that's really exciting because it's always felt like it's much more likely that in the brain it's displacement in and it's displacement out. And by kind of, what's that?
Sounds right.
Yeah, it's much more realistic in terms of kind of what neurons can do. And we were already, yeah, and it basically with this kind of change, we don't have to change anything about what's happening inside the learning modules. So, because you'll see at the moment, even though we get location in, we still calculate a displacement. It's still how we do path integration. But this simplifies things significantly here. But it also kind of opens up our thinking in terms of what the output of the column is. Because again, we often thought this was displacement, but then we kind of thought maybe it's a location because since we seem to need a location coming in.
For those who may not understand this, and there might be some judges. When we're talking here is like, does the brain talk about like, go to this location in space, or is it saying go in this direction at this speed for a certain amount of time? And the displacement is the latter one. It's like, move in this direction versus go to some location. You may know the location you're going to, but how's the brain, the brain actually, it has to integrate movement over time. So it's much more, it's got to be this way, for many reasons.
Yeah. And so there's still some details to work out in terms of like, okay, now we want to move an object through space. What is the nature of displacement? How are we displacing attention versus moving objects versus moving our limbs, all this kind of stuff. There's still a lot of details to work out, but it all seems a lot clearer now. And that was kind of a nice side effect of the voting stuff.
Yeah.
Does this mean this is a change to CMP as well?
Yeah.
Yeah. Okay.
Not happening at the moment soon.
Yeah, not right now.
No.
Yeah, for now we still have to think through consequences.
Right.
Well, we no longer send locations.
That's what I'm saying, yeah. So
Yeah.
that changes the definition of pose.
Well, you don't send pose anymore.
Or
Yeah, you don't
Set it
send
off.
location anymore, you just send displacements.
Yeah. We might still have orientation, but that would be kind of a separate thing.
And then, switching topics. And we can talk about all of these in more depth in the research meeting
Yeah,
too.
we definitely.
Interpretation.
So another question that's been discussed for months now, or over a year at least, robustness to deformations. So we can learn the model of a t-shirt or a sweater, or the model of a logo, and then the sweater can deform, the logo can deform on the sweater, and we don't have to learn a new model for all of the possible deformations. But the way we currently define our models are rigid models. Our models themselves can't deform. So that's been an issue so far.
It's sort of like, how do you recognize that the crumpled t-shirt on the floor is a t-shirt? Because it doesn't match any models you have with a t-shirt.
Yeah,
And yet,
right.
what is it? How do you solve that problem?
Yeah. And so a part solution, part of it we've already been working on. So Jose has been working on implementing a 2D sensor module, but we've really talked about it more broadly now, how it can be used to kind of tackle deformations, is to basically transmit different movements in different dimensionalities and use lower dimensional models that are immune to deformations. So for example, for this logo on the sweater, if you have a sensor module, instead of sending how it moves through 3D space, it communicates how it moves on the surface of the sweater. So basically in 2D space. Then how you move on the surface of the sweater is unaffected by whether the sweater is crumpled or not. You always move the same way on the surface, and that means the outputs of the sensor module will give you the same model and let you recognize the same model, no matter how crumpled and deformed the sweater is. And then similarly, an example in another dimension, if you have like a cable, if you just use our standard sensor module that tells you how you move in 3D space, that's pretty much impossible to match to a specific 3D model of the cable you have. But if the sensor follows the cable and basically transmits the 1D movement along that cable, if you go backwards or forwards on the cable, then you can learn and infer a 1D model of the cable in any deformed state that the cable might take.
And it really fits with like how, if you think about how you would understand this cable if you were looking at it, if you look at it and your eyes jump from here to here, you don't have any sense of how you've moved along that cable. because you don't model it in 3D. I mean, I guess you maybe have a temporary model that tells you you're kind of now on this side of the crumpled cable. But if you move slowly along it, you really have this sense of like, okay, this is how I'm moving through this lower dimensional space.
And this is where I should expect the end, and this is where I should expect the beginning of the cable.
Right. And I think one thing that's exciting about it is like we've always had this issue that we use reference frames, and reference frames are inspired by grid cells, and grid cells have this kind of rigid structure. There's like a little bit of evidence they might deform slightly and all this stuff, but there was never kind of convincing evidence that they were kind of in that sense that they would deform and move in the way that we expect objects to constantly deform. And with this solution, we can keep that assumption. We can keep the fact that grid cells represent a rigid structure. It's just that they represent a rigid structure in a lower dimension that's robust to these kind of changes.
I don't know if you have a picture of this, but if you think about how we think about t-shirts, most of our models of t-shirts are two-dimensional. We've learned what the t-shirt looks like when it's printed on a piece of paper. And so we teach our kids and so on. So it turns out we actually have a 2D model of the t-shirts, but it exists in 3D. And so we just explained how it is you move between those two models, right? You recognize it using the 2D model as your sensor is moving through 3D space. It just answers the questions how that happens. You don't need to learn new models of the t-shirt all crumple. You just need the one and figure out how to move through it.
Yeah.
Do we need to learn like a model of the, or like a temporary model of the deformation so that you can make predictions for the morphology? Like where would this feature be?
No, you don't really separate model.
Well, you could learn, as in you could learn a temporary model, say, of the current configuration of the t-shirt in 3D space.
To interact
that's what you
with
mean,
it.
to
but you
interact
don't
with
need
it, like
to predict
Yeah.
anything about the logo, for example.
right.
I mean, it's like looking at the cable, right? Could you learn that as a morphological model of you could, I could study that and stare at it for a few hours and then you could show it to me again. And I'd say, oh, that's the cable. Look, when it's squished like that. So that might be useful, or even a temporary model like that might be useful, right? So for example, what if you wanted to trace where you were halfway along the cable and you saw where you were, you could remember that and come back to it. But the point is you don't learn permanent models like this because these things are always changing.
And you don't need it to recognize the cable in the first
You don't need
place.
to recognize the cable.
Or predict that you're about to get to the end of it and stuff like that.
You can imagine doing the stuff I would do a lot of in the dark, like you pick up cable and you don't know where you are on the cable, or you don't even know which cable it is, but you do know if you follow along, you pull it, stretch it out in front of you, you're moving somewhere distance along the cable, you start to have a sense where you are. If you feel a feature on it, then you do know where you are, that kind of stuff. Or the same with a t-shirt, you might pick it up and it's still some scrumpled form you can't even see, but by following some edges of the t-shirt, you know that you're moving along this edge in 3 space, but you're also moving along the edge in the 2D space. And so that you'll know that. What's that?
With that
Yeah,
light thing.
Yeah,
I can think
yeah.
of it.
Cable tracing.
Yeah, so when we were doing the group team activity called in Prison Island, there was one room where a bunch of cables were coming out and you had to trace a couple to get the solution. And it was just these kind of pipes that are kind of all overlaid, but you could trace one at a time and see if it's going under something or over something and go until the end, so pick the right,
And it's a general purpose idea of
Yeah.
going between 2-dimensional spaces and how you map the two. And in essence, you should have a regular form of every object. And then if you agreed on the regular form of every object, even if it's lower dimensional, then you can work with them.
What's interesting about this is how good we are in navigating and operating in 3D space, but all our conceptual things are always 2D for the most part.
That's really interesting. We didn't talk about that. There's an issue about brains we didn't really talk about. We assume that brains can represent 3D space using grid cells, but the evidence for that is weak. And we didn't really explore the idea very far. Could this be how grid cells map everything in some sense? I think that's related to what you just said. It made me think of that. So that's for another day. But there's a powerful mechanism.
The power of the 2x2 grid.
Right.
Big concepts, right?
Right.
Cool. But yeah, so just so we don't take up too much of our time slot, move on for now. So just briefly to say, this doesn't solve all of the deformation problems. So you could still, if you have a 3D deformation and you don't have a 2D model of it, you just have a 3D model. We couldn't deal with that. Or if you have the 2D model of the logo and stretching it out, the 2D model couldn't do it anymore. It only works if you can have a lower dimensional model that recognizes the object. And so we talked about a couple of additional solutions that we could use to kind of get it working in any scenario, but we didn't settle on a full solution there. We can talk about those in a research meeting.
And then another big idea we had was, just around better understanding affordances and both kind of clarifying language around that, but also just clarifying how we expect learning to happen. So this is, a problem that we encounter where, we see an object in the world, it might be relatively unfamiliar, but we can interact with it as if it is seemingly really familiar. So, I want to pick up this box. I may have never seen this one before, but that's kind of trivial. And so what is it about our representations that enables us to do that? And the basic idea was that we have models that we're learning, for example, in visual cortex. These could be morphological models or behavioral models. And we have models in motor cortex. These are behavioral ones that are particular actions like gripping or pinching with your fingers. And when we interact or see someone interact with an object like this, we can learn basically two things at the same time. One is learning a causal link. So these are causal links like we have in general that we've discussed in the case of goals and stuff, that in order to have a particular behavior, we're going to rely on this model here. But in the case where this causal link is to motor cortex, we're kind of defining this as affordance. And this is in some sense a choice of language, but just to kind of make it consistent with how we tend to talk about the term affordance. So we're going to learn this causal link, but at the same time, often we're going to learn a new model, and this is the new model that's actually going to form this causal link. And this is going to be actually a really simple model in many cases, where we are attending to where kind of interactions are happening with this object. So you can imagine with this cardboard box, whether you see someone else do it or you're doing it yourself, you're attending to the fact that these are the kind of parts of the box that are being picked up. There's this kind of opposing motion. And that's literally all you need to represent in this model. And so in this case, this is a form of a morphological model. And what's kind of powerful about this is this morphological model can be reused in many instances and linked to many other objects. And so what we think is kind of happening when you see a box like this is, even if I haven't seen that exact box before, I'm recognizing a model like this that I've already developed from picking other similar objects up before. And that's what's able to recruit my motor cortex to tell me, yeah, this is how you should move your hand in order to pick it up. We spent a lot of time this week thinking through details around like, okay, now you want to kind of grip your hand. How do you get your hand into the right position? What do you do after you're touching it? How much force? How do you then move the object? There's a lot of detail there that we're not talking about here because we haven't kind of figured out all the details, but things like now we're outputting displacements rather than locations and things like that, we think are going to help with kind of filling out the final details around this.
And yeah, this was kind of cool because we didn't plan to talk about affordances, but we just got on the topic, and then after a couple of hours, we're like, did we just solve affordances? And
So,
yeah.
I just, sometimes people think of affordances often as like some visual aspect of a product that suggests what it's used for. Right? This explains all of that. It says, if I've seen someone interacting with the visual aspect of an object, what I'm doing, I'm seeing a motor behavior that I recognize, like twisting or poking or pinching. I've seen that actually on the object itself, because I've observed mom or dad do this, whatever, or some of your coworker do it. So I know where the affordance is on the object, is where the action occurred. And at the moment, I can then immediately associate that part of the object with if I ever see it again, it'll link back to the behavior. So if I see that something looks like a handle, it will automatically invoke, or at least make you think, or prime you to use the behavior to access that object, even if it's automatic. You don't really have a choice in the matter, right? And And so sometimes these affordances could be invisible, like you magically have to touch some capacitive panel someplace, or it could be a knob or anything, or it could be the sides of a box, parallel sides. So it really doesn't really introduce any new models on the left, but it says, oh, I can create a new morphological model, either this whole object or subset of the object that is an affordance. It's associated with a behavior. And if I see that morphological piece, I'll link right to the behavior. And then the other issue about, we solved a lot of the issues about how your hand moves to that. And it does it. So I think it's a huge deal for me because like, oh my God, I really thought about this.
And we think also that these affordance models would naturally be hierarchical, as in like you would naturally learn child or kind of associate child affordances, like just the fact that there's a surface and things like that. And that when we're interacting with a more unfamiliar object, kind of breaking down the series of actions you need to achieve something.
Well, not if the object is unfamiliar, but if the standard affordance behavior isn't available to you,
Right.
like if you can't pick up the box with your hand,
Right.
you could figure out how to pick it up with 2 sticks
Right.
Yeah.
by using the affordances of the child
Right.
object.
And basically break it down that way.
Yeah.
And we also walk through all the issues about like how you see the thing that the affordance, you know, how does the brain know how to move the hand up to that location, right? So, because now you know the location where it has to be, the pose of where the behavior has to be, which is the grasping behavior. So there's a lot of details behind this. But if we think about really building robotic systems that manipulate the world in a very flexible way, this is an absolutely essential component of that. And it's really nice to feel like, oh, we got the basic idea. This is right. Not gonna be wrong.
Yeah, you can see we're a bit excited because we're taking way longer than we should. This is a short one. Did you want to do that one? Or?
Sure. Yeah. So just briefly, this one, in some ways, it's a subtle distinction, but it's also an important one. We talked a bit about kind of language around goals and kind of clarified that with goal states or kind of goals, we're going to refer to getting the state of an object into a particular state. Whereas we also have this concept of kind of where an object is in space and its pose or its orientation, and that would be more of a target pose. And so I say it's subtle, but it's significant because we think kind of how this is being implemented and what kind of systems are involved might be quite different. And so there was like a lot of confusion maybe earlier in the week because we didn't have this kind of separation in the language.
This has been confusing for years. So we might say, move this laptop on the table over here. And you might say, the goal is to move the laptop on the table. No. You might have a goal of opening the laptop. That's a state change of the laptop. But moving is not a goal. It's a target pose. And there are different mechanisms. And if you don't use the different languages, you get confused all the time. So we have to separate out those two parts. So a clarity that makes, oh my God, finally we can have language. We can talk about this thing. Because it's so confusing.
Yeah. And lastly,
I'm going to do the last one here. You can see how much effort I put into the slide. I didn't make it.
I didn't.
I'll just leave this as another big area that we've always dealt with. In the brain, there's the neocortex, which we model the cortical columns. There's something called hippocampal formation, which is sort of the end of the neocortical sheet. It looks very similar in structure. The whole thousand brains theory is the idea that the structure in the hippocampus was replicated many times in the cortex. So we've known a lot about it, and the hippocampus is this very fast learning structure. We know that anytime you learn something quickly, it starts in the hippocampus. Yet at the same time, it ends up in the cortex. And so what is the relationship between these two? How do they interact with each other? When I'm learning new things, like where I'm learning the arrangements of items on the table and I want to move them, clearly that's the hippocampus, but the objects themselves are not in the hippocampus. So how does this all work? It was very, very confusing. So if you look at this picture here, this is, you're gonna get the raw data here. Well, on the left is cortical columns, and the right, there's two cortical columns on the left. They don't look like columns, but those two rectangles are cortical columns on the left. And the two boxes on the right are cortical columns, equivalent cortical columns in the hippocampus. I won't go into more detail than that. But what the basic idea here is, we already have this idea that an object ID can invoke object IDs in other columns. That's the voting mechanism. So what we're going to do here is we're going to have object IDs in the cortex, invoke object IDs in the hippocampus. But the model itself may not in the hippocampus, but if the object idea itself can anchor a reference frame, it's like a seed. Now I have two models of an object. I have the one in the cortex and the one in the hippocampus. The one in the hippocampus is unpopulated. It has the right reference frame, but it doesn't know what's in it. And so as you observe things in the world rapidly, it'll assign things to the object reference frame in the hippocampus, because that's quick memory. It's very fast to learn things. So when I say, oh, I remember where this is and that is that on the hippocampus. And so when I actually want to manipulate this world, manipulate the world, I'm going to manipulate both of these at the same time. I have the pre-learned aspects of the object in the cortex and the novel pieces in the hippocampus, and they're tied together. And now all of a sudden we can do all kinds of great things here. We can take existing models and add features to them. We can take existing models and move the components around. We can do new arrangements of things and know that the features still have the same properties. I won't go into the details, but the basic idea we figured out how we think we have a really good idea how the cortex and the hippocampal system works. It's more than I talked about here. And that's going to free up the whole aspect of living in a dynamic world where things are changing, where today Monty doesn't do that, right? Today Monty works in a rigid world. So another big idea.
Yeah, like maybe some examples of that you may have heard us talk about before, like, you know, what if you have a familiar mug, your favorite mug, your TPP mug, whatever, and it suddenly gets a chip in it? You know, how do you model that without having to entirely relearn this thing? But, you know, then you can still recognize a normal TPP mug if you see it.
Or even a mug that temporarily has a tea bag in it.
Right.
And I remember, oh, that one has a tea bag in it. That's not a permanent model of the mug. But I have to remember that right for today because I left it in the kitchen and I need to clean it. I know that I did that. I was lazy. I didn't put it in the garbage, you know.
And often we've kind of,
how do we do that? But still a mug. But
Right.
now how do I know it has a tea cup in it? But only that one, that kind of stuff.
and often when we've talked about that, it's been kind of just at the scene level and just this kind of weak, like, okay, yeah, everything's just in a scene. But this is much richer because there's this kind of corresponding hierarchy in the hippocampus that can be also kind of more detailed, like, oh, okay, where are things relative to this table? So
I think this is our last one.
Identify the words. I can only identify OBJ
ID?
object.
Don't worry about
Okay.
that. Don't
Feature.
those words are bad.
Feature.
What the only thing you need to know is that this is like this little the gritty
Yeah, I
thing.
saw that. Yeah, I
The
get
little gritty thing in the two upper boxes, I'll speak it out for the people online, are reference frames. The two black lines going back and forth are IDs. So object IDs, it's the same thing we use for voting.
Okay.
There's more to this picture to understand it that we didn't draw in there.
Okay, I just
So-
I saw footer and I was like, what is footer?
No,
feature.
that shouldn't even be featured. This is a child object to that object. This is the child object to this object. I shouldn't use the word feature. We changed it later. Anyway, I think that's our last line. Is it?
Yeah, last slide, and yeah, we went significantly over time. So
Sorry.
yeah, I think Terry and Celeste, you'll have a difficult choice to make. Before you reveal the winner, maybe we reveal the prize.
Oh, okay. Maybe that'll change our minds.
It might change their mind of who wants to win.
So, what is the prize? It is not just a spam can. It is a spam can with a 3D printed organizer thing.
Wow.
That
Pencils and
you
stuff?
could use for pencils, you could use for flowers. Someone mentioned you can make a nice
Wow.
flower with a spam can.
Wow.
Oh, man.
Now that I'm seeing this.
Man, I think you ought to award that to the judges.
We also ate the
So the-
spam
So the
yesterday.
envelope was 3D printed tops. Yeah, these are
That's
the
very
cans.
cute.
And in fact, one lucky winner
Uh-oh.
is gonna go away
Still full.
with a full spam can that they can eat.
And then
And then
to an organizer.
Turn into because yeah, I don't know if you saw Celeste and Terry, but we actually ate 2 cans of spam this week.
Wow, very impressive.
Did you eat
We
it?
ate it all.
We saw it in the refrigerator.
There was like 2
We finished
slices
this for
left.
breakfast.
Yeah.
Wow, very impressive, you guys. Okay,
Arrangement, that's pretty cool.
so I'm going to tell you what, I mean, it didn't take Terry and I long, but this was really, really difficult because as you probably realize, all 3 of those demos were amazing, but were like very, very different, right? Apples and oranges, especially the last one, the research versus more engineering focused one. So they were all very different. And Terry and I, we pointed out that the first one was kind of like a big problem that needs to be done. That's more a little bit internally focused on the simulator. The second one, a problem for our user base and the community. And the third one, you know, figuring out how the brain works. How big is that, right? And research. But we decided to award the prize to number 2, the config prize. So let me tell you why. It's because both Terry and I, you know, we're not researchers and we're not software engineers, but we both know that a big theme of this coming year is making it easier for the community to get involved and making it easier for them to understand. And I've had definitely my own experience with configs of stuff. And I think Tristan may know this, but I've had multiple friends of mine who are software or technical people attempt to run experiments on TBP and were unable to get it to work. And then they email me and try to get me to explain why they can't configure it or whatever. I actually enlisted Tristan one time and I think he helped me. I forget what it was, but then I just gave up and said, okay, we're going to fix this eventually. And this is huge, right? I mean, that configuration change is huge. The tool that you did, Ramy, amazing, right? It's really, I think, an incredible tool for our community that's going to be pretty short term, hopefully, to have an impact on a lot of people using this. So anyway, but the whole thing, you guys are amazing. This whole demos really proved to me what a great team this is. And it's just lovely to see everything you guys did. And seeing Jeff and Niels and Vivian together in a room, incredible. Maybe you guys ought to move to like some third place so you can be together all the time. And incredible.
You didn't see the time we were hitting each other over the head with the
intense discussions.
Yeah. But it is impressive on how much you guys got done in just a week. It's just amazing. I mean, it's I don't know. Plus you guys had also some fun times. I mean, you guys got to go do some things. So I think being, you know, and maybe it's because you don't see each other and aren't in the presence of each other that, you know, getting it done so much in condensed time actually works. I mean, if you knew that you had more time to do it, maybe it wouldn't have gotten done so quickly. So maybe the format also helped get so much done.
Right.
Yeah, it's been really impressive. Like each team, just the amount of work that happened in this 1 week and the amount of progress.
It seemed like this is really leap. I wasn't at the Brighton one, but from my impression, this is a really successful week.
Yeah,
Everybody.
I agree.
That's
Just-
awesome. It's awesome.
And also just, yeah, really nice to spend time with each other, get to know each other better.
Right. Well, thanks to judges. Thank you, Terry.
Yeah,
Thank
thank
you.
you.
Yeah.
You're welcome. It was such a pleasure to watch
Yeah,
everything.
no, I like it because it's all condensed. I didn't have to sweat for a whole week through it all.